Hi, and welcome back. In this lecture, we start talking about how to program GPUs with CUDA. This is the first of 3 lectures on the basic concepts of CUDA. At the end of these 3 lectures, we will be able to write our first CUDA program. But let's start with the first lecture about CUDA. In this lecture, I want to introduce the CUDA terminology and workflow and describe how to move data between GPU and CPU memories. I would like to stress 4 main points. First, CUDA has its own particular terms to express traditional concepts. Second, to develop an application to run on a GPU, we will follow the CUDA workflow that consists of 3 phases: move data to the GPU, compute on the GPU, and move back the results to the CPU. The third point is that we use CUDA malloc to allocate memory on the GPU. Finally, as a fourth point, to move data between GPU and CPU and vice versa is achieved by copying from a GPU memory location to a CPU memory location with a CUDA memcopy. When starting with CUDA, it's important to realize that NVIDIA introduced specific terms to express traditional concepts that have different names in other contexts. Big companies like NVIDIA and Google enjoy introducing new terms for old stuff. I'm not really sure that I'm sharing the same enthusiasm these big companies have in changing the names of things. However, it's important to know about these terms, as they are now widely used in the literature. First, we already met the term host, that means CPU. Second, GPU is called device. Third, you might heard the term kernel, that is a function executed on the GPU by a single thread. Fourth, we use the term launch to express the fact that the CPU instructs GPU to execute a kernel. Finally, an execution configuration is the definition of how many threads to run on a GPU and how to group them. When developing a new application or when porting an application from CPU to GPU system, it is convenient to follow the CUDA workflow. The CUDA workflow is the series of steps we need to do during the application development. The first step is CPU to allocate memory on the GPU and move the input data from the CPU to the GPU memory. The second step is CPU to instruct the GPU to execute a code in parallel. The third and last step is to move back the results of the computation from the GPU to the CPU. As we saw in the previous slides, the first step of the CUDA workflow is to allocate variables on the GPU memory. This can be achieved by using the CUDA function, CUDA malloc, that takes 2 arguments, a pointer to a pointer, and the size in bytes of the linear memory allocated in the GPU memory. I want to emphasize 2 points about this CUDA malloc. First, we use a pointer to a pointer to allocate memory on the GPU. That is different from the C malloc that returns a pointer to the allocated memory. I'm not going to details why CUDA malloc used this pointer to pointer, but I'm wondering if the NVIDIA computer scientists could have come up with a more elegant design solution. The second point I want to make is that in CUDA, when we provide the size of an array, we provide the size in bytes. If C is not your mother tongue, you might find this also a bit unnecessary complication. So how do you do in practice the memory allocation? Let's take an example of allocating an array called A of type double with 20 elements. We first declare a pointer, d_A, and we use CUDA malloc with the address of that pointer. Remember the pointer to pointer thing. And also remember to give the size in bytes of the array with 20 elements. That will likely be 20 times 8 bytes, that is typical size of the double. When I use CUDA malloc, I usually forget about the ampersand before the name of the pointer. So be careful with that. As typically in C and C++, CUDA doesn't have a garbage collector that takes care of the memory management. So we need to remember to deallocate memory once we don't need it anymore. For doing that, we use CUDA free that frees the device memory space that is no longer in use. This is really like the free functions in C. So I don't have a word of caution about this. When we talk about moving data from CPU to GPU, we are actually more talking about copying from CPU to GPU. To copy data from the CPU memory to the GPU memory, we use the CUDA memcopy function. The first argument of the CUDA memcopy is a pointer to the destination memory. The second argument is a pointer to the source memory. Then we have the size, again in bytes. And finally, we have the value CUDA memcopy hosted to device. In the example on the slides, we first allocate A on the CPU. we fill it with some values, and finally we copy A to the GPU memory with the CUDA memcopy function. Here, remember to allocate d_A first with the CUDA malloc. In the last part of the CUDA workflow, we move back the results of the computation on the GPU memory to the CPU memory. I think that you have already realized that to do that, we can use again CUDA memcopy and just change the value of the last argument to CUDA memcopy device to host. So we reached the end of the first CUDA lecture. I'll first introduce some terms of the CUDA jargon that is useful when reading GPU literature. I've then described the CUDA workflow, that is the series of steps we follow in designing an application for GPU. I focus then on the first and the third step of the CUDA workflow that involves data movement between GPU and CPU memories. We allocate memory on the device using the CUDA malloc function, and we move back data by using the CUDA memcopy function. In the next lecture, we will focus on the second part of the CUDA workflow, that is how to run a function, kernel in CUDA terminology, on a GPU. We are done with this lecture and talk to you in a bit.